Today we're doing exercises. All righty, let's see. So here is, so we are in nonlinear 2D ODE systems. That's what we're doing. Equilibria and stability. Okay, of equilibrium. All right. So here is an example. So let's call it a pedestrian, meaning, you know, very down to earth example. Okay. So here, let's study the equilibria. So find the equilibria and classify their stability for the following system. So there you go. Here is this system. Okay. So this is an ODE system. So we have to find the equilibria and stability. All right. So what we have to do, right, is one, okay, find the equilibria. Okay. So how do we do this? Meaning, do the right-hand side equals 0. So this is easy. We have y equals 0. And then we have to solve minus y plus x minus 1 times y minus 1 equals 0. Well, this means that y is 0. And from the second equation, we end up with x minus 1 times minus 1, if you want, is 0. In other words, we have the equilibrium, it's just 1, at, let's say, x e y e equals x is 1 and y is 0. Yeah. So obviously the second equation here has the solution x equals 1. Okay. 2, okay, we have to find the linearization. In order to study the stability, we find the linearization of this particular system. Okay, so find the linearization, okay, at x, e, y, e. So this means that we have to do, right, L, let's say, of x, y, and then we're going to put x and y is 0, 1, or whatever is there. That x, e, y, e equals 1, 0 equals, and now we take the derivatives, and so it's 0, right? So this is dB dx, and this is dB dy of the functions that are up here. So this one first, and then the second one is that one. Okay. So we have 0, the dx of y is 0, and then we have a 1 here. And now for this one, right, it will be what? It will be a y minus 1, but then we'll have to put it at x is 0 and y is 1. And then the other one is a twice, so we'll have a minus 1 plus x minus 1. And again, we have to implement the numbers. Yeah. So this is at x is 0 and y is 1. Yeah. Okay. So you guys put the chat there if you don't understand something, because that's exactly what I'm gonna, I'm gonna ask you in your test. Okay, so this is backwards, 1, 0, 1, 0. Yeah? Okay. All right, so now I'm gonna flip the page. So L at, if you want 1, 0, I'll write it directly now. So this will be 0, 1, and let's see what was on the other side. So I'll have a minus 1 here, yeah? and then a -1 here. Yeah, okay, I hope I'm correct. Yeah, there you go. Okay, all right. So now we have to do, so this is L. So next is eigenvalues of L at the equilibrium, right? Right? That's what we have to find out now. So we have to do determinant of L in 1, 0 minus lambda I2, okay, equals 0. So in this case, is determinant of minus lambda 1 minus 1 minus 1 minus lambda equals 0. So we end up with minus lambda minus 1 minus lambda plus 1 equals 0, or lambda squared plus lambda plus 1 equals 0. So we end up with lambda 1, 2 being minus 1 plus minus root of 1 minus 4 over 2. So there is lambda 1, 2 is minus 1 plus minus I root 3 over 2 if you want to. Let's write it separately. Right? Minus a half plus minus I root 3 over 2. And now at this stage, however you want to do this, okay, you can either use that table, you know, seeing here that you have delta negative, and it was, so this is the table path, right? Right. In that table, if you look directly at the equation, you have delta is negative, and then we have Q, I think it was the product, right? Lambda 1, lambda 2. This is 1 is positive, and P, which is lambda 1 plus lambda 2 is minus 1 is negative. And you deduce from this one that actually this is an unstable equilibrium, okay? And it's actually an unstable spiral, okay? Actually, I shouldn't put it in a bracket. I put it nicely here, okay? So this is an unstable equilibrium, and what type of instability is an unstable spiral? And if we are to do a drawing, okay? So if this is X and Y, and the equilibrium is at 1 and 0, right? So X was 1, Y was 0. So we put it here, okay? This is an unstable spiral. And so remember, the system was X dot equals Y, Y dot equals blah, blah, blah. And why do I do this? Because I see when Y is positive, X dot is positive, so X is increasing. And I'm doing this on a you know, on the idea that I have to, here I'm doing an unstable spiral, but I have to know how I'm going to put the arrow, right? So here, unstable spiral means that this guy is going out. Actually, it is green. Okay. And the arrow is this way because when Y is positive, X is increasing. Okay. So this is using the table in the book. You know, for me personally, how I'm thinking that X of t, it's something like E at minus 1 over 2t cos root 3 over 2t, blah, blah, blah. So this already tells me, so if you want, so this is, and Y of t is something similar. So I should make, okay. E at minus 1 over 2t sine root 3 over 2. And this already tells me that this kind of stuff will have a behavior that rotates, and then, oh, why did I say unstable? Oh, because I'm silly. It's stable, right? It goes in. right? In the table. It's just, I'm thinking somewhere else. Okay, fine. Fine. Boo. Okay. So again, this is going out. No, it's going in because it's stable. Okay, it was green. Okay, there we go. It's going in. Okay. So when I'm looking at this, see, I don't know how to use the table. I just know the theory behind it. Right? So the exponential kills everything. So it goes to zero, right? It goes towards the equilibrium, and the cos and the sine are just doing the waving, right? The rotating part. Okay. So there you go. Okay. So there's this is a standard exercise. So what you see here, right? It's really, so if you want, this would be the, let's make room nicely here. You don't have to do anything. I'm just writing it nicely. Okay, and that's to make room for, decide on stability. Okay, so there are 4 points to be covered, right? So the first one is, right, find the equilibria. The second one, find the linearization at the equilibrium. The third one, decide on the eigenvalues, compute them. You can use Maple, you can use whatever you want. And so this is third, and fourth is the stability in itself. So use the table or use your knowledge, whatever is more convenient for you. Okay. There, if you Google, I bet there are tables that are even better than the one that is in that textbook. Right? So this is so standard that it's out there big time. Yeah. So this is a kind of a standard exercise that I expect that everybody will know how to do, right? I mean, it's very clear what it is to do. Now, let me show you how one can make this exercise a little bit more complicated, okay? So I'm going to call this complications. Right? I mean, it's an open textbook, right? So if it's open textbook, I have to look for things that would make things a little bit less obvious, right? Okay, so here, I'm going to modify is the same system. So the initial system was like this, right? Yeah. So this was initial system. Okay, I'll make it more complicated. I'll put here an A, where A is a parameter that is not zero. And the requirement will be find the equilibria and discuss their stability. Okay, as A belongs to R, less zero. Okay, so in other words, do cases, right? Is a parameter. Right? So we have different cases. As A is positive and A is negative and stuff like that. So, the steps in principles are the same, right? So first we're going to do the equilibria, right? In other words, we're going to do right-hand side equals 0. So we have A, Y 0 and minus Y, whatever, right? Equals 0. And the long story short, we end up with the same point, right? So it will be 1 and 0 because A is non-zero, right? So Y has to be 0. So it's exactly like the other one. So it's a nice complication that I'm doing. I'm not making it horrible. Right? What will change the linearization, right? So when we're going to do L at 1, 0, right? It will be almost like the other one. Instead of 1 will be an A. And the rest is the same. So what was that? -1 and -1. Right? So now when we do the eigenvalues, so we do det of L, right, equals 0, we end up with minus lambda, minus lambda, minus 1, or -1 minus lambda, as we like you do it. Okay, and then plus A equals 0. So in other words, we end up with lambda squared plus lambda plus A equals 0. And we have to discuss this equation, the roots, as A is a parameter that can be positive or negative, right? I see, and that's where it stuff, it gets complicated. So, the complicated, it's a little bit more than what was before, right? So I have to keep in mind that A is in R, but is non-zero, right? Actually, it would be interesting to study what's going on at 0 as well, right? But that's even more delicate. Okay, so now what I'm going to do, I'm going to do first the discriminant, right? And it's clear that, now I have to distinguish between delta positive. So this is when 1 minus 4a is positive. In other words, when a is less than 1/4. And in this case, I'm going to end up with lambda 1, 2 to be -1 plus minus root of delta, basically. Actually, in this case, it's easier to do it with P and Q, right? So Q was lambda 1, lambda 2. So in this case is A, right? And now we distinguish between if Q, which is A, is positive, then lambda 1 and lambda 2 are real and have the same sign, right? And in this case, we're going to have P that is lambda 1 plus lambda 2, and in this case is -1 is negative. So this means that lambda 1, 2 are real, and have the same sign, and the sign has to be negative. And so looking at the table, we deduce that 1, 0 is a stable equilibrium. It's a stable node, or what I want to call a sink. Now, the other case, so this is to be recorded, right? And then at the end, so this is, we are in the case when A is less than 1/4, but is positive. At the end, we'll have to make a table with our result, right? Now, the other case is if Q, which is A, is negative, then lambda 1, 2 are real and have different signs. And in this case, again, P, which was the sum of the two, is -1, is, oh, well, we are not interested actually. That's irrelevant in this case. So we're going to have one is positive and one is negative, right? So in this case, again, we're going to look at the table and deduce that 1, 0 is unstable and it's a saddle. Okay. Actually, maybe I should do this one. So this is the big one that we're dealing with, okay? In truth, right now, if we're doing, yeah, okay. So let's do this classification here. So let's call this case A, okay? And I'm gonna flip the page to case B. Okay, ready? Okay, so that's the equation. Okay, so case B is when delta, which is 1 minus 4a, is 0. In other words, when a is 1 over 4, in which case we have lambda 1, 2 to be actually minus 1 over 2. Okay, so lambda 1, if you want, equals lambda 2, and this minus 1 over 2 because delta is 0, right? So lambda 1 is negative, lambda 2 is negative. So again, in this case, we have a stable equilibrium. And if you look in the book there, right, it will be a degenerate stable node, or degenerate sink if you want. And finally, when delta, which is 1 plus 1 minus 4a, is negative, right? Right? In other words, when a is greater than 1 over 4. So we should do this like this. Okay. All right. So in this case, lambda 1, 2 is minus 1 over 2 plus minus I root of, if you want, absolute value of delta or minus delta. The point is that it has the I there. Again, you can look in the thing, right? So in this case, we're gonna have that 1, 0 is stable equilibrium, and it is a spiral. Okay, so node. Okay, what was the name? What I'm always okay. Stable spiral. There. Right. Okay. So in conclusion, now we have to conclude, right? In conclusion, okay, we have if. So now I'm looking at these cases, right? So I'm starting from minus infinity, right? So if I'm looking at the a-axis, okay, what are the points of interest? Is 1 over 4, and it's 0, right? And that's it. Huh? Okay, so we have one interval here, one interval here, and one interval here. And in each one is something else. Maybe I should do the conclusion like this. This is a nicer way to represent this stuff. So this is a axis, so the parameter axis. And as I said, we have 0 and we have 1 over 4 at points of interest. Yeah. So we have for a in between minus infinity and 0, we have a saddle. Okay, so here it's a unstable. Oh, I should write it. And it's a saddle. Okay. Then in between 0 and 1 over 4, was a stable node, stable, okay? And it's a, well, I like to call it sink, okay? And then here is stable as well, and it's a spiral. There you go. And we have to decide on the edges. Okay, so the edges here, oh, A is never zero actually. So there you go. There's no A in there. So this is a hole here. Actually, I'll make it with a hole in there. Okay, and with this one, okay, so when is 1/4 at the general, okay, so yeah, I can say here also this is degenerate, okay, node, okay, and this is stable as well, right? Something. I'm trying, guys. Right, it's with this guy. Okay, I guess it's clear enough. All right. So you can see how easily these problems can become complicated, just like that, right? It's enough to put a parameter. And in full, disclosure, right? This changes, that happens when a parameter goes over a threshold or another. This is the subject of what is called in dynamical systems bifurcation theory, and is very interesting. These are bifurcation points, like A equals 1/4 or A equals 0. I just avoid it just because it gets kind of weird there, and you're still at the beginning, so there is no point to push I don't know what on you right now. But you get the idea that the fact that when a parameter changes, the behavior of the system can change, and this leads to this idea that this understanding that little changes can cause huge catastrophes, right? And this is in relation, if you want, to climate change. So it's this thing called actually catastrophic theory. And one of the one of the, in a way, corny examples in this theory is that, when a butterfly, spread its wings, in South America somewhere, this can cause later a hurricane up on, on North America, right? Little changes can cause huge changes, right? It's possible always for something like this to happen. Okay. So this being said, let's do another example, right? So that's all what we're doing today. Here I have another one with a parameter, which I will call mu this time, not A, okay? So here, so here's this exercise. Okay, so the requirement is the same. Okay, discuss equilibria and their stability as the parameter changes. So here is this system, mu minus x dot is mu minus x squared, and y dot is x minus y, and mu is a parameter, a real parameter. Okay. Yeah. Okay. So the things start with equilibria actually. So calculating the equilibria, right? So we do the right-hand side equals 0. So they start being different from the first lines, right? Okay, so the second equation, yeah, x equals y. But the first equation, right, says x squared is mu. And this one can have or not solutions as mu is positive or negative, right? So it's right there. If mu is greater equal than 0, then we're going to have x equals plus minus root mu, right, as equilibrium, right? And then we're going to have x e y e to be plus minus root mu, and y is still, right, because x equals y, right? Whereas if mu is negative, then there are no equilibria. Ta-da. And actually, you know, this can be represented on an axis, right? So let's say this is the parameter axis, and this is the equilibria axis, and we have something like, right, for mu positive, we have xe is plus root mu, and then xe minus root mu, right? These branches of equilibria, right? So we can say 1 and 2, I don't know, xe1 if you want, and xe2, because there are two branches, right? And no equilibria when x is negative, right? So there we go. Okay. For every mu fixed positive, right, you're gonna have two equilibria. And actually this kind, so basically at mu equals 0, there is a bifurcation going on. Okay. Bifurcation point. Okay, let's call it like this, right? And this, so the point is not in the phase space. That's why I avoid to say bifurcation point. Bifurcation value, let's call it value, not point. Okay. And this kind of bifurcation, because there are more kinds, right? It depends on the powers of x, you know, x at 3, x at 2, x at 1, right? This is called to be, yeah, well, I won't give you the name actually now. Maybe I'll do the representation next week sometime, okay? So just leave it like this. Okay, so it's a bifurcation value there, okay? At mu equals 0. Okay. All righty. So now this being said, the exercise is still not over because we have to do the stability, yeah? And this is done, okay, so this is to be solved, if you want, only for mu greater or equal than 0 when there exists, okay, equilibria, yeah? Okay, so, right, we have these guys. Okay, so we have to do the linearization, right? So we have to do L at xCye, right? So again, we are doing dBdx and dBdy. So this would be a minus 2x, right? And then it's at xCye, right? Okay. All right. And then this is a 0 here. And then we have here a 1 and here a minus 1. Yeah. So basically, right, there are various ways to write this thing. So this will be minus plus 2 root mu, 0, 1, and minus 1. Right. Okay. And now we're doing eigenvalues. Okay. Okay, so this will lead to minus, okay. So we have to solve minus plus 2 root mu minus lambda, 0, 1, minus 1 minus lambda is 0, right? The determinant. So we end up with minus plus 2 root mu minus lambda times minus 1 minus lambda is 0, and blah, blah, blah. Lambda 1 is minus 1, and lambda 2 will be minus plus 2 root mu. Okay. So let's put them together now carefully, right? So at plus root mu, we have lambda 1 is minus 1, and lambda 2 is with minus, right? It's important. Okay. So in this case, we're gonna have that this is a stable equilibrium, right? Because they're both negative, yeah? And it is a stable node or a sink, okay? And then at the other guy, we have lambda 1 is minus 1, and lambda 2 is plus 2 root mu, it's positive. So this will be an unstable equilibrium. It is a saddle. And actually, we can represent this on in the parameter space. Okay. So if these are the two branches, remember? So we have that the positive one, it's unstable. So I'm going to make it dashed. So this is unstable. It's unstable. It's a saddle. Okay. And this, I'll make it full. And this is stable. Oh, no, it's backwards, right? Okay. So this is stable. And this is unstable. There's the saddle. And this is stable. It's a sink. Okay. And if we are, so this is in the parameter space. If you want. Equilibria in the parameter space. Okay. And now if I want to draw the phase space, right, we had these two equilibria, so I'm going to squish it into here. So in the phase space, if this is X, this is Y, we had one here, let's say, so for mu positive, yeah? So we have root mu. So one equilibrium is up here, and the other one is here. Minus root mu. And now if I want to do a drawing, right, this is a saddle. Which one? This is a saddle and this is a sink. So for this guy, everything comes in from all directions. Okay. Whereas for this one, well, some are coming in, some are coming out, right? So there will be two principal directions, which are given by the eigenvectors at the unstable equilibrium, at the saddle, but I won't compute them now. But, you know, if we compute them, we can just do the vectors here as they will show up and then figure out who's who and what is what. So let's do it with light green. Okay, like we did last time on an example, right? The point is that on one is coming in and on one is going out. So I'll say, look, it's going out on this and it's coming in on that. I'm not sure which is which, but that's just a guess. And then, you know, to draw the trajectories, they're doing something like this. Okay, and that's all what we can say for this system with the knowledge that we have right now.